Welcome to lesson 3, where we will be talking about complex numbers. Our objectives for this lesson are to define what a complex number is, our second objective is to plot complex numbers on what are called an Argand diagram. Or, in other words, the complex plane. And our third objective is to work with complex numbers and the conjugate of a complex number. To define what a complex number is, we really need to work with quadratic equations, because the first time we see complex numbers or imaginary numbers are with quadratic equations. The quadratic equation x squared plus 1 equals 0. If I'm trying to solve this equation, what am I going to get? I'm going to get x squared equal to minus 4. Then I'm really looking at x as the square root of this minus 4 with a plus or minus in front. Now, until today, we said, I'm sorry, you got to stop here. You say that there is no real root to this equation because you can't take the square root of negative 4. Well, it turns out you can. You just need to define a different kind of number as your solution. So to define what square root of minus 4 is going to be, we need to first define the square root of negative 1 as I. Now, I, or the square root of minus 1, is the imaginary unit. Okay? It's called the imaginary unit. And once I have the imaginary unit defined as I equal to the square root of negative 1, then I can say, well, I think I can just factor this minus 4 as minus 1 times 4. I'm going to call the square root of minus 1 I. So I'm going to have an I out front, and I have the square root of 4, and I know that's 2. So my solutions are 2I and minus 2I. Well, numbers of the form b times I, where b is a real number, are called imaginary numbers because they are the imaginary unit multiplied by a coefficient. So numbers of the form bi are called imaginary numbers. Now let's take a look at this equation. X squared plus 2x plus 5 equals 0. This is another quadratic equation. Our first instinct is to try to factor this, but we find out we can't. And remember from a previous work that you would use the quadratic formula. And the quadratic formula said minus b plus or minus the square root of b squared minus 4ac all over 2a. Now, the coefficients here are a equals 1 or 2 for b and 5 for c. So when you plug these in, you get negative 2 plus or minus the square root of 2 squared minus 4 times a, which is 1, and c, which is 5, all over 2 times a, which is 1. Now, when we simplify this, especially the discriminant inside the square root, we get the square root of minus 16 here, all over 2. And then we can say the square root of negative 16 is no other than 4i, so we can say negative 2 plus or minus 4i all over 2. And then we can distribute the 2 and we get negative 1 plus or minus 2i. So we have two solutions, negative 1 plus 2i and negative 1 minus 2i. These two numbers are complex numbers. They are of the form a plus bi. Okay? They are of the form a plus bi, where a and b are real numbers. Okay? From this, we can see that if b is 0, you just have the number a, which is still a complex number. So real numbers are special complex numbers. They are a subset of complex numbers. And imaginary numbers themselves are complex numbers as well. They are just the case when a is 0. Okay, so all the numbers that we've seen so far were actually belonging to this superset of complex numbers. Okay, one thing we can do with complex numbers is to identify their real and imaginary parts. Now, when we got a complex number, we label it with a z. Let's say we have a complex number in the form a plus bi. The real part of z is the part that doesn't have the imaginary unit. So it's the coefficient a. For instance, if we're looking at this complex number 2 plus I, the real part, let me call that z, the real part is 2, and the imaginary part is the coefficient before the imaginary unit, or I. So the imaginary part of my number z is simply b, and in this case the imaginary part for 2 plus I would simply be the coefficient before I, which is 1. Now when we plot this complex number in the complex plane, we plot the real part along the horizontal axis and the imaginary part along the vertical axis. So altogether we will be plotting the point 2, 1. Okay? So that will be the plot of my point of my complex number z in the complex plane. Okay, let's say we want to plot another point or another complex number, minus 3 plus 4i in the coordinate plane. What that means is I'm going to plot the point negative 3 and 4. Okay? So the point negative 3, 4 refers to my complex number, negative 3 plus 4i. Now, based on this number, I can also define its conjugate. And the conjugate is going to be especially useful when we do division with complex numbers. We're going to use the conjugate of a complex number directly in the process of division. Okay? The conjugate is defined as with a bar over z, and what it does is simply negates the imaginary part of the complex number. So for this particular z, negative 3 plus 4i, the conjugate will be minus 3 minus 4i. And if I want to graph that in the complex plane, I'm simply going to mark the point negative 3, negative 4, and let's say that's the point here, so this marks the conjugate of z, or negative 3 minus 4i. Now let's do a more complicated type of problem. Let's find the square roots of negative 5 minus 12i. Okay, I'm going to use all these things that we've talked about so far with this question about a complex number, its real part and imaginary part. Let me say that z equals a plus bi. And by asking for the square roots, I'm simply looking for whatever z squared is equal to minus b minus 12i. So what I'm going to do is I'm going to take the square of this z. So I'm going to take a plus bi quantity squared, and I'm going to set it equal to minus 5 minus 12i, and I'm going to look for a and b. So when I square a plus bi, I get a squared plus 2abi plus b squared I squared. And I want to set this equal to minus 5 minus 12i. Okay? Now, because I is defined as the square root of minus 1, I squared actually equals negative 1. So instead of I squared, I can substitute negative 1, so I'll just have minus b squared here. Okay? Now the real part of the complex expression on the left-hand side is simply a squared minus b squared, and the imaginary part is simply 2ab. So what I can now say is a squared minus b squared equals negative 5, and 2ab equals negative 12. So from this, I get AB equal to negative 6. So now I've got two equations and two unknowns, and I'm looking for A and B. Now we're looking for A and B that satisfy these two equations. So let me try to isolate B here on the right-hand side, and I'll get minus 6 over A. And I can just plug this in here. So I get a squared minus 6 over a quantity squared equal to minus 5. This will give me a squared minus 36 over a squared equal to minus 5. If I multiply through by a squared and I transfer everything to one side, I'll get a to the fourth minus 36 plus a squared equal to 0. Let me rearrange that. So I'll have a to the fourth plus 5a squared minus 36 equal to 0. This will be factored as a squared plus 9 and a squared minus 4. So I can have a squared plus 9 equal to 0, or a squared minus 4 equal to 0. Here I get a squared equal to minus 9, and a and b were supposed to be real numbers, so nothing comes out from this end. Then I'll have a squared equal to 4 here, with a equal to plus or minus 2. And when I plug in a equals 2 here, I'll get b as minus 3. When I plug in a equals negative 2 here, I'll get b equal to 3. So I will have two square roots. My square roots will be 2 minus 3i with the coefficients 2 and negative 3, and also negative 2 plus 3i. So those are my two square roots. In lesson 3, we looked at complex numbers, where they came from with regard to solving quadratic equations, how we graph them in the coordinate plane using the complex plane or an Argand diagram. We also looked at the real part and imaginary part of a complex number and the conjugate of the complex number. I hope this lesson has been useful, and I'll see you in the solution video for worksheet 3.